Welcome to the lecture. My name is Sunain Jameel, and today we will see the pole zero placement method for simple IIR filters. So, what is the effect of adding poles and zeros in Z-plane? So, if we add a pair of complex conjugate zeros within on the unit circle, the numerator becomes this one. Its magnitude contribution, what will be the magnitude contribution? Its magnitude will reach 0 since this factor becomes 0 when omega is equal to theta. So if we add a complex pair of poles, the magnitude response will increase and frequency will also increase. So if we want to increase response, we will have to place poles, and if we want to decrease or reduce magnitude response, zero placement will be there. So this is the graphical representation. Magnitude response, and this is the magnitude response in denominator. So if we want to design a second order band pass filter, what we will have to do is to just calculate the magnitude. These factors R is the magnitude controlling the bandwidth, and angle theta is angle controlling the central frequency. So we will have to just apply these formulas, and after implementation of these formulas we will get a second order band pass filter pole zero plot like this one. Let's have another explanation. So what will be the response of the filter? It will be like k into z square minus 1 over z square minus 2 rz cos theta plus r square. So k is scaling factor here, and which is calculated by the following formula for this case. Let's have an example. A second order band pass filter is required to satisfy the following specification. Sampling rate is 8 kHz, 3 dB bandwidth is 200 Hz, narrow passband center frequency 1 kHz, zero gain at 0 Hz, and 4 kHz. What does it mean? It means that we have these central frequency, one central frequency at 0 Hz and the other at 4 kHz. They're asking us to find the transfer function using pole zero placement method. So just substitute the values in the formula, which is, first of all we will have to calculate R by using this formula. so it comes out to be zero point 0.9, which is less than 1, so filter is stable. Then the theta angle and k, after calculating all the values, substitute these values in the transfer function formula, you will get the transfer function of the filter or response of the filter. So similarly we can design a second order band stop or notch filter using the pole zero placement method. Only the difference is here the calculation of k and the response. In this method, while designing notch filter, k is equal to 1 minus 2 or cos theta plus r square over 2 minus 2 cos theta, and it will look like this one. 0 and poles are in the same direction or on the same line. Here is an example. Sampling rate is 8 kilohertz, bandwidth 100 hertz, narrow pass band, center frequency at 1500 hertz. Transfer function, will have to find transfer function. First of all, R will be calculated same as in the previous case. Theta will be the formula to calculate theta will be same in the previous case, only the difference will be in k and the transfer function. So we can design first order low pass filter using pole zero placement method. In this case, first we'll have to calculate alpha. There are two cases. When Fc is greater than Fs by 4, this one, the formula to calculate alpha will be the second, the highlighted one. So if Fc is less than Fs by 4, sampling frequency divided by 4, then the unhighlighted formula for alpha will be used, and transfer function of first order low pass filter will be k into z plus 1 over z minus alpha in this case. K is 1 minus alpha by 2 for unit base. It is called unit band pass gain scale factor. Here is an example. Sampling frequency is 8 kilohertz, cutoff frequency 100 hertz, zero gain at 4k hertz. Transfer function, we'll have to calculate transfer function. So sampling frequency, in this case sampling frequency divided by 4 is greater than Fc, so the first formula will be used. After calculating alpha, we will calculate k, which is 1 minus alpha over 2, and then substituting the value of k and the h of z, and we will get the response of the filter. Similarly, we can design first order high pass filter using pole zero placement method. In this, the only difference is alpha will be same. The only difference is h of z and k. In this case, h of z will be k into z minus 1 over z minus alpha, and k will be 1 plus alpha by 2, and graphically it will be like when fc is less than fs by 4, the filter will be like this one, the a figure, and if fc is greater than fs by 4, then the filter pole 0 plot for the filter will be like the second one. Let's have the last example of today's topic. A first order high pass filter is required to satisfy the following specification: sampling rate 8 kHz, cutoff frequency 3.8 kHz, and zero gain at 0. First of all, we will calculate alpha. Now, if we divide fs by 4, it comes out to be 2000, which is less than 3800. So the formula for alpha will be the second one, the second case, which is fs is greater than fs by 4. From that we calculate alpha, which comes out to be minus 0.8429. Then we will calculate k, unit gain scale factor, which comes out to be 0.07854. Then substituting these values in the h of z, the formula of h of z for high pass filter, which is k into z minus 1 over z minus alpha, we will get the desired filter transfer function. So that's it for today's lecture. Thank you very much for watching.